My name is Zach Meyers. I teach physics and engineering in DC, primarily to 11th and 9th graders. This is my 7th unit I've done here at YNI. And I find that the more and more I do these, the more and more I try to challenge myself to be creative and try to dig deep as far as having the opportunity to explore content that I don't normally have the time to explore, and especially with expertise here, colleagues, as well as the seminar leaders. This year, I delved into the world of tropical cyclones, something I had no familiarity with, but was obsessed with storms as a kid. I don't know, my favorite movie growing up was Twister. Do you guys remember Twister with the cows? And so I've always had like an obsession with tropical storms and like major weather events, and it's becoming more and more relevant as climate change becomes more and more ever pervasive in our daily lives. And I also wanted students to start thinking about physics as a foundation to understanding these complex problems. So, one of my pitches at the first beginning of my year with the kids is like, physics explains exactly why you're able to sit in your chair. How you're able to sit still. What you're actually doing at this moment is physics. And so they challenged me, and I'm like, what do you mean? What do you mean? I don't understand, Mr. Meyers. And I was like, you will understand. So this year I delved in the world of thermodynamics and how that is essential understanding how these storms form. I haven't given my unit yet, but I'm probably going to be implementing that sometime in the spring once we get over the basics of thermodynamics and what energy is. So I'm going to walk you through kind of an overview of what I plan on implementing in the spring, and then kind of giving some interesting ideas, physics concepts, and then what I'm planning on doing with my kids. Okay, so the title of my unit is Energy Dynamics of Tropical Cyclones, the Impacts of Climate Change. These storms are massive. You can see them from space, and oftentimes what happens is they generate a ton of energy. It's because they're circulating heat all the time. And the way they are able to do this is basic physics. The complexity is beyond the course of college and beyond the course of high school, but the basic understanding of how a storm generates is just purely convection, which we'll go over. Some things that I wanted to take into consideration in designing this unit was I always want the students to be able to apply basic concepts to some type of phenomenon. And in this case, the phenomenon is going to be tropical cyclones, hurricanes, typhoons. So that's going to be energy conservation. How is energy being transported within these systems, and how do we take that idea and concept and then relate it to this more broad scale phenomena? Discuss how energy is distributed in these how energy is transported in these systems. Again, heat is exchanged. How is heat exchanged? What are some basic thermodynamic principles that are interplay with these systems? And then analyze data, climate change data, to see if they can make predictions. So have them practice being scientists and kind of infer what they think might happen based on these principles and based on the current data set. So that's the overarching idea of the unit. We have NGSS in DC, and it's addressing that standard, developing using models to illustrate that energy at the microscopic scale can be accounted for by a combination of energy sources and transportation methods. So, what are tropical cyclones? So we in the States know as tropical cyclones as hurricanes. But if you're in Japan, you'll know them as typhoons. If you're in Australia, you know them as something completely different. But essentially, it's the same thing. It's a rotating storm that is based in a low pressure system that's basically circulating energy and growing based on a heat source, mostly in the tropics. Specifically, the conditions that require a tropical cyclone to form is warm ocean waters. Well, with climate change warming, that adds more fuel, more possibilities for tropical cyclones to develop, especially especially near the equatorial regions. The other thing that's really important is that these giant systems are circulating through the atmosphere, and if you've ever been in an airplane before, you'll experience turbulence. Well, there's a reason why you experience turbulence, because there's shear force winds that are acting on the plane that are causing it to be disrupted. And the same thing applies to these storms. These storms generate lots of heat, and the heat rises, and if there's shear winds up in the upper atmosphere, it's going to disturb that formation and cause that to dissipate. So there's special conditions that are needed for these things to arise. It's not just heat rise. There's a lot more nuance associated with it. And then also you need some type of atmospheric disturbance, often associated with low pressure systems. In our case, we see the Atlantic storms. The reason why we get Atlantic storms developing right after the Sahara Desert is because the winds from the Sahara act as condensation nuclei and allow water droplets to form. And so a lot of our Atlantic storms are based on the desert in Africa, which is kind of crazy to think that we can be impacted by that. So that's a little overview of what tropical cyclones are. And then here's how they're structured. So students are going to understand a little bit. I don't need them to understand the most complex idea of what these things are, but essentially these things function as convection systems. So the first thing I'm going to do is I'm going to put a lava lamp on my desk, and I'm going to ask them, explain what you see. So a lava lamp is a perfect example of a convection system. You see the little wax balls go up and then come down. Why is that happening? Well, it's the same principle of why you get these systems forming. You get adiabatic pressure, they're all forming, they go up and down. Again, these types of ideas are really, really important for them to understand and then apply it to here. Some other things to take into consideration is conservation of energy. So energy doesn't just spontaneously happen. Energy is basically heat. In this case, is the most primarily one that we're going to be talking about, and it's being exchanged through these current systems that are guided by convection. And one of the things that I want them to understand is essentially a tropical cyclone is a steam engine. You essentially have work being done based on heat being exchanged up and down through the system. And the same way you have heat rise and expand, the same thing happens within a tropical cyclone. As it goes higher and higher through the atmosphere, it cools off, then comes down into a sink. That actually does work, physical work, just like a steam engine does, which powers an engine. So these giant systems produce these massive quantities of work. And then we're going to talk about an overview of these three data sets. So one of the questions I have for the kids are, how frequent are the systems going to be? What type of intensity would you expect? And then also, how do sea surface level temperatures play into the fact that these storms are coming? Where they're going to be? Are they going to be impacting East Coast more often? The Caribbean? Why or why not? So we analyze those three data sets. And that is my time. Thank you.